Hi, welcome to Comfort Institute's series of instructional videotapes on carbon monoxide and combustion safety. Be sure to watch the other tapes in this series to gain an understanding of all the issues involved.
In the previous two videos, we discussed the combustion process and the health effects of combustion byproducts, especially carbon monoxide.
We discussed the many possible sources of carbon monoxide, including unvented combustion appliances, as well as other interior and exterior sources, such as attached garages. And we emphasized the importance of venting all byproducts of combustion out of the living space. When vented appliances such as furnaces, boilers, and water heaters don't vent properly, hazardous combustion byproducts, possibly including carbon monoxide, can enter the living space. While new research is finding that attached garages and unvented gas appliances such as gas ovens are more common sources of low-level CO production, when larger appliances like water heaters and furnaces don't vent, the result can be much higher and more immediately life-threatening levels of CO. Understanding the venting process and the many factors that can cause it to fail is essential for all those involved in inspecting and servicing residential gas and oil-vented appliances. By watching this video, you will learn the differences between the four categories of vented appliances as defined by the American National Standards Institute, the dynamics involved in the creation of proper draft and vented combustion appliances, and how combustion byproducts are exhausted from the building when vented appliances are drafting correctly, and the many conditions or events that can cause a failure of the venting process, allowing combustion byproducts to enter the indoor air. First of all, it's important to understand the differences in the ways various appliances are designed to vent their byproducts of combustion. The development of more efficient combustion appliances has resulted in many new designs that have different venting requirements. Therefore, in the late 1980s, the American National Standards Institute, ANSI, along with the American Gas Association, established criteria for designating vented combustion appliances as one of four categories. Field technicians should understand the definitions of these categories, as the category of each appliance is on the rating plate. This tells the technician the general venting requirements of every appliance. Third-party testing laboratories verify that the appliance operates satisfactorily according to the category marked on the rating plate. The ANSI categories, which have been part of the National Fuel Gas Code since 1987, that is Z21.47, and in Canada it's CSA 2.3, were selected based on two key venting characteristics. The first is the pressure produced in a special test vent, and the second is the temperature of the flue gases, which directly influences the potential for condensation in the vent system. At this time, only the American National Standards for gas-fired central furnaces, boilers, and industrial heating equipment have adopted these standards and require the listing on the rating plate. According to the ANSI definitions, a Category 1 vented appliance is one that operates with a negative vent static pressure and with a vent gas temperature that avoids excessive condensate production in the vent. Since the vent gases of Category 1 appliances are usually well above the dew point temperature, they operate with only a small amount of condensation being created. The traditional draft hood, dilution port, or barometric damper equipped appliances, such as this gas furnace, this gas water heater, this oil furnace, all have the negative pressure and flue gas temperature criteria of Category 1 appliances. A negative vent static pressure simply means that the pressure inside the vent is lower than the pressure in the combustion appliance zone, or CAZ. This negative pressure, or suction, is what draws both the combustion byproducts and dilution air from the combustion appliance zone, past an open draft hood, diverter, or damper, and on out through the vent system. If there were a crack or hole in the vent connector at this point, air in the combustion appliance zone would be drawn in there as well. In Category 1 appliances, the suction pressure within the vent system is created by the heat of the combustion gases rising up the vent. The gases are hotter and therefore more buoyant than both the ambient air in the CAS and the outdoor air, and so they rise, much like a hot air balloon. The gases leaving at the top essentially suck new combustion gases or dilution air in at the bottom to replace them. Category 1 appliances are often referred to as atmospherically vented appliances or natural draft appliances because the draft is not created by a fan. The strength of the chimney draft for Category 1 appliances is affected by many things. Here's an overview. Combustion gas temperature. Since the driving force for the draft is the heat of the combustion gases, the hotter the gases are when they leave the appliance, the stronger the draft will be. Partly because of higher flue gas temperatures, most oil-fired appliances have stronger draft than gas-fired appliances. An under-fired unit, possibly due to an improper orifice or gas pressure, may have low vent temperature and weak draft. Excessive airflow over the heat exchanger can also overcool the combustion gases and weaken the draft. Chimney height. The taller the chimney, generally the stronger the draft. To reduce wind turbulence problems, the termination must be above any nearby roof lines, typically 2 feet above any roof within 10 feet. This can vary, though, for B-vent, so always check the venting tables and your local codes. Outdoor temperature. The colder it is outside, the stronger the draft will be. Conversely, the warmer it is outside, the weaker the draft will be. Vent connector slope, length, and number of elbows. Friction in the venting system reduces draft. Single-wall vent connectors should ideally be short, have few elbows, and be sloped upwards at least 1/4 inch per linear foot, preferably more. The total horizontal length of the vent connector should be less than 75% of the vertical height of the entire venting system. Long horizontal runs lose heat and create resistance and are a common cause of weak draft. Thermally activated vent dampers generally restrict draft and are not recommended. Vent connector leakage. Any leaks in the venting system, such as at pipe joints, elbow gores, or a leaky cleanout hatch, will reduce the draft on the appliance. Vent connectors should at least be free of large gaps and should ideally be sealed with high-temperature silicone caulk. Here's an example of a particularly bad water heater vent. It is long, has a low slope, and even a negative slope for a certain portion. The single wall pipe and the B vent weren't even totally connected. Virtually all of the combustion gases were venting into the basement. Chimney location, construction, and insulation. Since the draft depends on the combustion gases staying hot, chimneys that rise inside the thermal envelope of the house draft better. The less single-wall pipe, the better. Pipe passing through unconditioned spaces should be insulated, such as Class B vent. Uninsulated masonry chimneys located outside the house's thermal boundary lose heat fastest and tend to have the weakest draft. Remember that a masonry chimney must have an intact tile liner in order to use that chimney to vent any appliance. An additional liner may be required depending on the appliance or appliances you wish to vent. Chimney cross-sectional area or volume. A properly sized vent moves all the gases quickly to the outdoors. However, some venting systems are undersized and some are oversized. Both can hinder draft. Always refer to venting tables for proper venting size. Also, see the Uniform Mechanical Code, Chapter 8. An undersized vent may not be able to carry all the gases. An oversized vent can cause the gases to rise too slowly, losing heat to the chimney and thereby weakening draft. One of the worst venting situations occurs when a gas furnace that needs, say, a 5-inch diameter pipe is vented into a tile-lined 8-inch by 8-inch masonry chimney. The volume of the chimney is greater than needed, and so the gases stay in the chimney longer than they should, cooling down dramatically and increasing the risk of draft failure, as well as flue gas condensation that can damage the chimney. Outside wind speed. Generally, the stronger the wind blowing across the top of the chimney, the stronger the draft. Exceptions exist when turbulence caused by nearby roof lines or trees forces a downdraft. Type of chimney cap. In general, a chimney cap helps ensure wind-induced downdrafts won't occur. Some caps are better than others at increasing the draft caused by wind. And of course, a crushed cap will cause friction and reduce draft. Chimney obstructions. Soot, birds' nests, squirrels' nests, offsets or bricks, tile fragments, and debris caused by physical deterioration will increase the resistance to flow and reduce draft or even stop it altogether. Masonry chimneys can and do break down, and condensation is a common cause.
Type of Category 1 appliance. Traditional atmospherically vented gas appliances with an open draft hood or dilution port are the most susceptible to draft problems. Oil-fired appliances and mid-efficiency gas furnaces with inducer fans are somewhat less susceptible. Heat exchanger obstructions or air leakage. A very dirty heat exchanger will hinder or stop the flow of combustion gases out of the appliance. Leaky or cracked furnace heat exchangers can either depressurize or pressurize the vent system, causing draft problems as well as incomplete combustion. Location of the appliance. Appliances located in the living space or garages are usually more susceptible to venting problems caused by negative pressures that are created by mechanical fans. Appliances in ventilated buffer zones, such as an attic or crawl space, are generally less likely to experience competing negative pressure caused by fans. They can still, however, have problems caused by wind or powered attic or crawl space ventilators.
Tightness of the combustion appliance zone. In theory, if an appliance is in a tight enclosed space and does not have intentional combustion and ventilation air openings, it can starve for air and draft will be affected. This is the reasoning behind code requirements for adequate combustion air openings. While codes have required this, in most cases when there is a downdraft or spillage problem, it is due to depressurization or venting issues rather than air starvation. And air starvation is often a misnomer. And last, but certainly not least, competing negative pressure. Category 1 appliances are designed to operate in an environment that has a neutral air pressure. A negative air pressure in the combustion appliance zone, or CAZ, relative to atmosphere will weaken or even completely reverse the chimney draft. Negative house pressures can be caused by many factors. Return duct leakage in an enclosed combustion appliance zone sucks air from that space. Any negative pressure in the combustion zone can weaken or reverse the draft in the venting system.
Outside air can actually be drawn down the appliance vent to feed the return air leak, stopping the draft altogether.
Another significant cause of negative pressure is other devices that draw air from the house or the combustion appliance zone. The most powerful are fireplaces and downflow kitchen barbecue exhaust fans or other commercial-grade exhaust fans. Next are clothes dryers and whole house exhaust fans. Smaller exhaust fans, such as in kitchens and bathrooms, can contribute to the problem. Any other vented appliances that use air from that space can also contribute to negative pressure problems. And even an exhaust fan outside the living area, such as a powered attic ventilator, can suck air from the house or CAZ. Generally, the tighter the house, the more likely negative pressures can be created by internal exhaust that will compete with chimney draft. When interior doors are closed, the main air handler fan can create pressure imbalances within the house. Areas that have more return than supply, whether intended or not, will go to a negative pressure. Different door closures often create a negative pressure in the combustion appliance zone. This is quite unpredictable and needs to be tested. Basement doors can have a major impact. So can bedroom doors in houses that do not have return inlets in all the bedrooms. Supply duct leaks in an attic or crawl space can depressurize the house and possibly the CAS, thereby causing draft problems. The wind and stack effect on the building can also create negative pressures in the combustion appliance zone. For example, code-conforming combustion air intakes on walls that are opposite the prevailing winds can actually suck air out of a CAS. So can combustion air intakes that come down from the attic through the house, if the heat from the house causes the air in the combustion air intake to rise into the attic. The normal passive combustion air openings are not one-way valves, and if a competing driving force stronger than the chimney draft wants to pull air out of the CAS through them, it will. In the winter, the house can act as a chimney as its warm air rises and competes with the appliance vent. This is especially a problem with tall houses that have a high percentage of their leaks in the attic floor.
As you can see, there are a great many variables that affect draft for Category 1 appliances. It's not uncommon to find many negative factors working together to create frequent spillage or backdrafting situations. In fact, many if not most appliances will spill for a few minutes on startup until the chimney gets hot enough and draft gets strong enough to carry out all the combustion byproducts. We'll go into how to test draft and diagnose and improve many of the above variables in more detail on subsequent videos in this series.
As we have mentioned already, the traditional draft hood and barometric damper equipped appliances, such as this furnace and this water heater, are considered to be Category 1. However, it is important to know that all mid-efficiency fan-assisted appliances are also Category 1. It is a common misconception that the inducer fan in these appliances is there to force the gases up the vertical vent. In fact, its role is solely to pull the gases through the furnace heat exchanger, which has more resistance than the open heat exchangers common to older style furnaces. Once the fan has pulled the gases through the furnace, it essentially dumps them at the base of the vent where the draft created by the heat of the gases is expected to take over. The vent gas temperatures in these mid-efficiency furnaces are designed to be in the same range as the older draft hood equipped models after dilution. It's possible for the pressure in a vent system connected to a fan-assisted appliance to be negative because once the draft has been established, the draft action should be stronger than the fan pressure rise if the vent is designed correctly. One interesting phenomenon that can occur with fan-assisted Category 1 appliances stems from the fact that they can be common vented with standard water heaters with open draft hoods. This is a diagram of an acceptable design from the National Fuel Gas Venting Code. The problem occurs when the fan-assisted furnace fires and the vent stack is cool. For a period of time, until the vertical stack can warm and establish a natural draft, the slight positive pressure created by the inducer fan in the furnace can backdraft into the building through the draft hood of the common vented water heater. If the water heater fires and attempts to establish draft at this time, it too can spill its combustion products into the building also. And of course, if the chimney or vent becomes blocked, this will occur continuously. Here we will take a quick look at this phenomenon with this type of common vented situation. This is a code-compliant setup with a fan-assisted furnace and a draft hood-equipped water heater, common vented into B vent through a Y connector. As we fire the furnace, we see the pressure in its vent connector goes to positive 0.02 inches of water column. The bottom number we see here on our analyzer. The top number, by the way, is parts per million of carbon monoxide. We see that we also have a slight positive reading of 0.01 inches of water column in the vent connector of the water heater. Here we are showing the air movement at the test hole in the furnace vent connector with a smoke puffer. Notice it's blowing away from the hole, indicating that under positive pressure the flue products will exit any openings in the vent. Here at the water heater draft hood we can see moderate spillage also using a smoke puffer. As the vent system warms, it should establish a natural draft to reverse this situation. And after 2 minutes or so, we see that the pressure in the vent connectors of both the furnace and the water heater are now negative 0.01 inches of water column. And the smoke now enters around the draft hood of the water heater as it should. This phenomenon seems to occur quite regularly under this type of setup, regardless of whether the water heater is connected to the common vent with either a T or a Y connector. Here's another example with a setup that is not completely code compliant. Here, a fan-assisted furnace in a workshop area has its connector pass through a wall. Here it is from the other side. Notice the lack of clearance between the single-walled vent connector and the sheetrock. This then enters a T connector above the entry of the common vented draft hood equipped water heater. This also is not code compliant. The smaller appliance, the water heater, should enter above the larger appliance, the furnace. We see the same phenomenon of spillage occurs here. As the furnace fires, we see the pressure in the vent connector is a positive 0.02 inches of water column. And checking the water heater draft hood with the smoke puffer shows total spillage. We also repeated this test with the water heater already fired for 2 minutes before we fired the furnace. We see once again that we have total spillage at the draft hood. That means the combustion byproducts of both the furnace and water heater spill into the home for a short period of time until good draft is established. In this example, it took approximately 4 minutes after the furnace fired until the spillage stopped and good draft was established. Although this type of common vented situation can be code compliant, as we saw in the first of our 2 examples, it does not mean it will not potentially spill combustion byproducts into the space surrounding the water heater. We at Comfort Institute feel that whenever an alternative method of venting these 2 types of appliances separately is possible, it is the safer choice. When you are testing or servicing an existing setup of this type, it is crucial that you test for carbon monoxide and recommend very strongly that the homeowners install carbon monoxide alarms to be safe from this potential problem. All Category 1 appliances, whether they are fan-assisted or not, should be vented using the manufacturer's installation instructions. The instructions may refer to the National Fuel Gas Venting Codes, which usually provide different options for various installation circumstances.
Although Category 1 appliances are normally vented vertically, certain ones may also be vented in unconventional ways, specifically horizontal through-the-wall arrangements, if a particular specified vent system is used. This actually then converts the appliance to a Category 3 type.
In these cases, the vent system must be supplied or recommended by the manufacturer of the appliance. Installation should also follow the manufacturer's instructions exactly. Category 1 appliances that have this venting option are listed in the American Gas Association directory as having a special venting option. One other particular type of Category 1 appliance is actually a sealed combustion unit. This is the type that is required for use in mobile and modular homes. This type of furnace vents directly through the roof vertically and typically does not allow the use of any elbows or offsets. All of the combustion air is supplied from outside the structure through either a duct through the floor at the base of the furnace, or as you see in this example, from above through a double-walled vent system. The flue products exhaust through the center pipe and exit from the top of the roof cap. The roof cap has a separate lower opening that allows combustion air to be drawn in through the outer space between the 2 pipes and is even preheated by the heat from the combustion products passing through the inner pipe. All combustion heating appliances in mobile homes must be rated for use in a mobile home and be of the sealed combustion type. Although fireplaces are not listed under the ANSI categorization system, it is useful to know that most fireplaces would fall under the Category 1 classification. They have both a negative vent pressure caused by the rising hot combustion gases and high flue gas temperature, and they are therefore subject to the many draft problems experienced by Category 1 appliances. Later videos in this series describe in further detail the fundamental design criteria to adhere to when designing a new vertical Category 1 venting system. Later videos will also expand on the issues to consider when evaluating the performance of an existing venting system, including negative pressure in the combustion appliance zone. We'll now move on to the other three categories. ANSI Category 2 appliances also operate with a negative vent static pressure, but with a cooler vent gas temperature that may cause excessive condensate production in the vent. There are few, if any, Category 2 appliances in the residential market. We will not be discussing Category 2 systems any further on these videos. Next, let's discuss Category 3 appliances. Category 3 appliances operate with a positive vent static pressure instead of negative, but still with a high enough vent gas temperature to avoid excessive condensate production in the vent. A positive vent static pressure simply means that the pressure inside the vent is higher than the pressure in the combustion appliance zone. In Category 3 appliances, the positive pressure in the vent system is created by the fan in the appliance. If there were a crack or hole in the vent at this point, combustion gases in the vent would get pushed out into the combustion appliance zone. An example of a Category 3 appliance would be a mid-efficiency furnace that is vented horizontally through the wall. As we described earlier, some Category 1 appliances may be converted to a Category 3 appliance if allowed by the manufacturer and if the appropriate venting materials are used as described by their special venting options. However, the requirements to do so are very specific in that you are now relying on a relatively weak positive pressure that is established by the inducer fan in the appliance. The requirements for doing this are very specific and the manufacturer's directions should be followed exactly. Another example of Category 3 appliances would be fan-induced power shot gas-fired water heaters, such as these from the A.O. Smith Company. These can be vented horizontally as the vent system is under positive pressure and the flue gas temperatures are reduced by the additional dilution air drawn in by the fan, rather than being reduced by a secondary heat exchanger, as is the case with high-efficiency appliances. These are an unusual type of Category 3 appliance. Because of the lower flue gas temperatures in these specific appliances, certain types of plastic pipe are allowed for venting. However, most Category 3 appliances can only be vented using stainless steel seamless vent products now because of the still high flue gas temperatures. In fact, there is a national program in the U.S. called CAP, the Corrective Action Program, whereby manufacturers have replaced the original plastic vent pipe specified on Category 3 appliances. This was done because of a history of problems with deterioration and loosening joints in the plastic pipe. This could be a very serious issue since these systems vents are under positive pressure and any openings will spill combustion byproducts into the building. Because the vent connected to Category 3 appliances, as well as Category 1 appliances that are converted to Category 3, operate at a positive pressure, they require an airtight vent system to avoid leakage of flue products into the building. Remember that plastic is no longer allowed for use on Category 3 appliances. An exception would be the power shot type of water heaters mentioned earlier. Also, for residential installations, horizontal venting through the wall should never use traditional venting materials such as Type B or single-walled galvanized vent pipe. These traditional products that are not gas-tight should only be used for venting systems that are primarily vertical and will have a negative vent pressure and must be sized according to the manufacturer's instructions. Once again, always adhere to the manufacturer's guidelines when venting any of these appliances. Category 4 appliances operate with a positive vent static pressure created by the fan in the appliance, just like the Category 3 appliances we just looked at, but with a lower vent gas temperature that may cause excessive condensate production in the vent. The typical 90% plus efficiency sealed combustion gas furnace is an example of a Category 4 appliance. These appliances need an airtight but also very corrosion-resistant vent system that includes a method of condensate disposal. Category 4 appliances are usually high-efficiency condensing models. The combustion gases have been cooled by the appliance's secondary heat exchanger to a point where additional condensation is likely to occur in the vent. And most are sealed combustion two-pipe units. in that they draw all combustion air through a pipe from the outside of the building, although not all are. Since the venting system is largely isolated from the house, especially when using two pipes, the common spillage and backdrafting problems experienced by Category 1 systems rarely occur with Category 3 and 4 systems. Nonetheless, manufacturers' instructions and tables must be carefully followed, notably the common requirement that the total equivalent length or friction resistance of the two pipes be roughly the same. Since the pressure in the vent of a Category 3 or 4 system is positive, they cannot be common vented with a Category 1 appliance. If one were, its combustion gases would be pushed out of any open dilution ports or draft hoods. The fan-induced positive pressure in the vent would typically cause the Category 1 appliance to not vent at all. Category 3 or 4 appliances cannot even be common vented with another Category 3 or 4 appliance. The fact that you cannot common vent a Category 4 appliance, such as a 90% gas furnace, with a Category 1 appliance, such as a standard natural draft water heater, is well recognized by the trade. However, a commonly overlooked requirement is that when a new 90% furnace is installed in an existing home, the old standard water heater must be revented with a smaller diameter vent. Many problems can arise from simply leaving the water heater connected to the old, now oversized vent. As we reviewed earlier, Category 1 appliances must be connected to a properly sized vent, not too big and not too small. When a water heater is left connected to the existing vent that used to serve both the water heater and a furnace, we often see very weak draft, continuous spillage, CO production, condensation in the vent, and dangerous deterioration of the vent caused by the acidic condensation and freeze-thaw cycles. This is especially a problem with chimneys that are outside the thermal envelope or already oversized or poorly insulated and were weak to begin with. These water heaters are often called orphans and are a growing problem given the greater acceptance of high-efficiency sealed combustion furnaces. In fact, a class action suit has been launched against a Michigan utility and its installing contractors who put in large quantities of these furnaces without addressing the water heater venting. Here is an example of just that situation. This new high-efficiency furnace was installed and the water heater was left connected to the original 6-inch B vent that had also common vented the old furnace. Notice the staining from condensate dripping out around the B vent and over the connector and new cap. This has all occurred in just 1 month since the new furnace was installed. At Comfort Institute, we strongly recommend that you not ignore this problem when installing a replacement high-efficiency furnace. Either revent the water heater or sell and install a new Category 3 sidewall vented water heater. Another option is to recommend a combination water and space heating system that uses one vent. So that covers the 4 ANSI categories of vented appliances. To review, Category 1 appliances include practically all traditional vented appliances that either have a draft hood or a barometric damper, as well as all mid-efficiency furnaces with inducer fans that are connected to conventional vertical chimneys where the draft in the vent is negative caused by the heat of the rising gases. Residential Category 2 appliances don't currently exist, so we don't discuss them here. Category 3 appliances use a fan to induce a positive pressure in the vent, but run hot enough that condensation in the vent is unlikely. Typical examples are sidewall direct vent water heaters and converted mid-efficiency fan-assisted furnaces. And Category 4 appliances use a fan to create a positive pressure in the vent, but run cool enough that vent condensation is likely. A typical example is a 90% condensing gas furnace. This example is a Category 4 furnace, but it is not sealed combustion. Here are the burners. Categorizing appliance designs is important for 2 reasons. First, this determines the size, type, material, and installation requirements of the vent system for a particular appliance. For example, Category 3 and 4 appliances both require gas-tight vent systems since the pressure within their vent systems is positive. A Category 4 appliance will require a vent system built of corrosion-resistant materials since condensate is corrosive. Masonry chimneys are specifically not acceptable. On the other hand, Category 1 appliances may use traditional venting products such as Type B vent pipe or masonry chimneys within the recommended limits of the National Fuel Gas Venting Codes. The second reason it is important to categorize appliance design is that it better identifies the appliance's potential to spill combustion byproducts or be subject to backdrafting or possibly even flame rollout. The draft in Category 3 and 4 appliances, the vent systems of which are under positive pressure, is generally driven mechanically and dependably with a fan. These units also have a pressure sensor that will shut the system down if the correct negative pressure is not indicated at the inlet of the fan housing. However, in the previous example of a Category 1 fan assist type furnace that is common vented with a water heater, its pressure sensor won't operate because the system can vent out through the draft hood of the water heater. So the fan is still able to draw in combustion air at the normal pressure. By and large, Category 3 and 4 appliances are much less susceptible to many of the venting problems Category 1 appliances often experience. Many Category 3 and 4 appliances are also sealed two-pipe systems that are not affected by negative pressures in the house. For all these reasons, it is normally not required to test the draft on Category 3 and 4 systems. Also for these reasons, as a general rule, Comfort Institute recommends sealed combustion Category 3 or 4 equipment use over Category 1 systems. Increased safety is in fact a greater benefit than the lower utility costs. However, since Category 1 appliances use the air surrounding them for combustion and venting, and because they often have a draft hood that, when venting poorly or not at all, will allow combustion byproducts to enter the indoor air, it is particularly important that we inspect and test these appliances very thoroughly and ensure that they vent properly. There are three distinctly different events that can occur when a Category 1 appliance isn't venting properly: spillage, backdrafting, and flame rollout. Spillage is defined as some or all of the combustion byproducts backing up into the building by spilling out of the draft hood or diverter. Spillage can be either for a short duration, typically at the beginning of the cycle while draft is still being established, or it can be continuous, usually due to either a blocked vent or backdrafting. For this reason, we at Comfort Institute discourage the use of mechanical vent dampers in that they tend to increase the amount and length of time of spillage at startup. This is because they are closed and blocking the vent until they warm up adequately. Electronic dampers, on the other hand, must open prior to the gas valve opening, so they do not contribute to spillage at startup. Spillage has the potential to create very high levels of carbon monoxide. If the spilled combustion byproducts that didn't vent get drawn back into the burners, these contain a high carbon dioxide level and low oxygen, which causes incomplete combustion and creates carbon monoxide. While most Category 1 appliances will spill for up to a minute on startup until the vent gets hot, many will spill for up to 3 or 4 minutes at the start of most cycles. Since many furnaces may only run for 5 or 6 minutes each cycle, a very high percentage of the total combustion gases can end up in the living space. This is not healthy and should be remedied. When a complete reversal of airflow occurs in the vent system and outside air flows downward into the building, the phenomenon of backdrafting occurs. This outdoor air being sucked down the appliance's chimney is typically providing makeup air for whatever has induced a negative pressure in the combustion appliance zone. A powerful generator type exhaust fan, the clothes dryer, return leaks, whatever. If the appliance fires during this condition, all the combustion byproducts will spill into the CAS. Carbon monoxide could be produced in large quantities, and draft may never get established during the cycle. The third phenomenon that can occur is flame rollout. At a sufficient negative pressure, the flames can actually be pulled out of the front of the burner. This obviously dumps all the combustion byproducts into the building, but it creates a real fire hazard as well. Here's an example of a water heater that has experienced flame rollout. A sure sign of this having taken place is telltale black soot deposits on the outside of the unit in proximity to and above the burner area. You may have seen this before on combustion appliances. Another sign is burned up wiring above the burners on a furnace. Of all the Category 1 appliances, the most susceptible to spillage, backdrafting, and flame rollout are natural gas or propane furnaces, water heaters, or boilers which have draft hoods or dilution air ports that are open to the CAS. Newer mid-efficiency gas furnaces, as mentioned earlier, usually have pressure sensors that lock out the system if a positive backdrafting occurs. While safety is usually maintained, it does create what may be misinterpreted as an unexplainable nuisance trip. And remember that if the furnace with a fan inducer is common vented with an atmospherically vented water heater, and a backdrafting or blocked chimney situation occurs, both the water heater and the furnace's combustion byproducts will spill out through the water heater draft hood. Oil furnaces and boilers typically have barometric dampers that make them less prone to spilling combustion gases to the inside. However, these units can often cause soot and odor, and sometimes cause noise complaints as well. In addition to spillage, backdrafting, or flame rollout, weak vent pressure can also affect carbon monoxide production because vent pressure dictates combustion air intake. The system can only draw in the same volume it can exhaust. If an appliance is not drafting properly, this can also negatively affect the combustion process, causing it to be incomplete and to create more dangerous combustion byproducts, specifically carbon monoxide. Therefore, in addition to removing the combustion byproducts from the building, proper venting is also critical for complete combustion to occur in the first place. If too much or too little combustion air is provided, this can negatively affect combustion and hence the efficiency of the system. For all these reasons, testing draft pressure in all Category 1 appliances is imperative and is a fundamental part of a complete combustion safety testing protocol. How to correctly measure and interpret the draft of Category 1 appliances is covered on a later video in this series. We will also cover repair and correction for many of the problems you will encounter with combustion appliance venting. So, in conclusion, remember that this video is not intended to replace manufacturer and code specifications and requirements for venting systems. Always follow the most current manufacturer's installation specs and local code requirements when selecting venting products and designing a venting system. Be sure to take the quiz that accompanies this video to make certain you have mastered the information. And we'll see you next time.